Yeah. So yeah, today I think as Akash mentioned, right? So we are going through this paper known as AliBi, and it is like why we should care about this paper is one simple thing, right? That let's say all the models that you train right now, right? Those are limited by the context they are trained on, maybe like the full sequence length, and you cannot extrapolate beyond that. Or at least in some models where they support this extrapolation, the problem is it only supports like maybe till let's say X number of tokens, and probably that after it fails. And there's this problem like dealing with document level task, like document level models. So those are pretty, mm, I would say, close to zero or at least pretty less in the field. And yeah, so this paper at least tries to maybe revive those or at least certain extent, I would say, by introducing this positional encoding method where you can extrapolate to a higher sequence length as well. So that's at least high level idea of the paper. And just to mention like why we should care about this paper. So I think everyone of you might have heard about Bloom. So Bloom paper uses alibi positional encodings. So that's one thing at least like why this might be an interesting method and have been adopted for like really big models. So probably it's worthwhile at least spending some time and maybe see what might be like next coming through this as well further on. And yeah. So in this case, if we look at right, so what Alibi does is like one simple thing in like overall the method is very simple and it's just one to maybe trick that they use like or change compared to the existing methods. So they add positional encoding information or positional information directly in the attention scores. So that's the difference, and they skip the positional encoding at the start. So that's TLDR or high level summary, I would say at least of this. And at least the model or the proposed idea of alibi relies on the fact that the tokens which are closer to the context should be like basically attended or at least should have high inductive bias, and the ones which are like farther should be basically scaled down at least and maybe like should have lower uh, what I mean, attention scores, or at least somewhere where we have some dispositional information injected together. So that's the one. And yeah, feel free to interrupt if you have any doubts as well. So probably if we look at RNNs, right? So RNNs are basically the ones where we have they take one input sequence at a time and process, right? So it's more like a chain way, like basically unfolding. So in that, probably if we look at, they don't suffer with problems such as like positional encoding because that's inherently encoded in their nature or at least like the model design. But if you look at like basically the transform architectures, they are bounded by the sequences they are trained on at least, and it's very hard to basically let's say general build a model which can generalize on the longer context like than they were trained. And yeah, so that's one paper like this paper tries to go over. And at least RNNs, although they don't suffer let's say this problem, but there are other problems such as long-term dependencies and yeah, forgetting and all. So that's one area to yeah. So that's one in this, and yeah. So one simple way we can think of like let's say what would be the way to maybe extend this thing. So if we look at like from probably the transformer architectures, right? So people have tried maybe positional encodings like learned as well as static positional encodings. So static would be maybe sinusoidal. Anyone? Okay. Which problem could you repeat maybe once? What problem maybe if you're talking about? So
Yeah, so yeah, so you just mentioned that RNNs don't suffer from this problem and what this problem is in this context.
yeah, so RNNs don't suffer from positional encodings, right? At least because if you look at you process one thing at a time, right? So in a way, your information positional encoding information is captured, right? At least. But in a sense, in transformer, right, you do parallel processing and like everything attends to everything, right? Like one, so you can
Mhm.
attend to every token, right, in the past. So probably it becomes very hard to basically manage and like direct information, right? So you have to inject positional information additionally in the embeddings. So that's one
Okay.
thing. Like let's say RNNs do not have like or like don't suffer, but RNNs do suffer with the problem of long-term dependencies. So as you like let's say move as you have longer context, then probably like let's say whatever that might be encoded at the early might not be reflected in the current position. So they have this problem of forgetting because of the limited memory they can hold. So that's the idea at least and the problem. And yeah, this paper at least tries to solve that. So how can you deal with longer sequences and like process those? So the point being that how can you come up with positional encodings that are not dependent on the sequence length? Uh, okay. And yeah, so one simple approach, let's say we can think of, right? So originally the authors propose the vanilla transformer authors propose like two methods, right? One is like basically the static embeddings methods where the sinusoidal, and next is like basically let's say this learned embeddings where they learn some embedding representation and then basically yeah you add that to the model, like, and that's learned throughout the training process. So one of the problem with like learned embeddings is that you are bounded by again the sequence length that the let's say model has learned, and you cannot like basically extrapolate to the like those embeddings. The other thing in the sinusoidal is that like let's say it's a sine wave function, right? So you can probably extend this to longer sequence as well. But based on I think empirical evidence, at least like that this paper says that it is very difficult to extrapolate with sinusoidal positional embeddings. And I'm not very sure why this might be. Maybe one reason at least, but that's very yeah, I need to still like know more about it, but might be that the dimensional space might be very constrained till in this case, and maybe it might require more complex functions to map out this positional information, or at least yeah, some way. That's one way I can think of probably. So yeah, there are different positional encodings. So probably I will go about this like T5 bias as well. Sorry about this. Yep. But so far that's the best method that is out there, and yeah, in terms of extrapolation. And yeah, so alibi, I think I will talk about this probably in later on part. Like they just add this biases to this attention score computation and like yeah, which are proportional to the distance like between relevant key and query. So if we look about let's say why we should care about this paper,
Sorry,
right?
I just had a quick question. Yeah, about the sinusoidal thing. Could you explain again, like why it's giving poor performance or that? Could you just repeat that part again? I was a bit confused.
Yeah, so I'm also not quite sure about this part. The authors didn't like maybe mention much details, I would say, but at least one maybe case would be that this function might be still limited in the way that since like the sine waves have like a fixed amplitude, right, and maybe that sort of representative capacity might be limited. But still, which is very hard because you have n dimension n sinusoidal waves, so eventually we'll get a unique pattern. But you're not sure why like we see on this part much. Yeah, because this paper haven't like explored or at least like provided much evidence on like why this might be the case. It is right now you can consider more of an empirical evidence, I would say, probably.
Yeah, I think what the authors are trying to say is that the architectures that use sinusoidal position embeddings as an input to denote the position of tokens, they don't really scale well, and they are not really discussing why that happens, because generally, yeah, sinusoidal position embeddings are used in transformer architectures, and though they don't really, their inference is not very good for very huge sequences.
Yes. Yeah, that's one case might be. Yeah. So I hope
Okay.
that answers probably your question. But yeah, I think maybe I'll find more as well and get back on this. So the next part, like at least why should we care about this paper or at least work? Would be if you look at this diagrams, right? So what this does is like let's say when you train a language model, right? So you evaluate language models based on some measure, and here it is perplexity, and lower the better. So probably if you look at different methods that are out there, right? So sinusoidal, if you look, it's just like when you move a bit like higher sequences itself, like it directly explodes like a lot, which says like that it's very it cannot extrapolate to longer sequences and not very reliable. There are other methods such as rotary embeddings and T5 bias, which I will talk about a bit in a while. And if you look at those, at least comparatively perform better, but still those also like at certain maybe tokens, they also suffer this problem of like exploding. Like perplexity is like starts to increase, and but in alibi if you look, so even if you let's say train a model on 5 into sequence, right, you can still like basically see that the perplexity line is completely or almost flattened, and you can like basically kind of preserve same perplexities when also doing like evaluation or inference on like higher token sequences, which is very good trait I would say in models, because then this opens up like more opportunities. Like let's say you train very small sequences, but you can like still manage to do very well on the bigger sequences and maybe deploy these models for those applications as well. And same applies for maybe 1024 tokens as well. But if you look at in this case, the bias DeFi bias is a bit, at least like decrease, the perplexity is a bit lower, but still yeah it increases like with time or tokens. And yeah, for alibi it's still small or at least like consistent. So that's like the one motivation or at least like reason why we should like probably go into this paper. And next thing, let's just talk about, yeah. And if you look at this particular method as well, right? So what they do is like they just add the positional encodings, right? So eventually you're not learning or at least storing some coefficient. So you save upon memory, and maybe that kind of also gives you speed up in training as well. So there are two types of training speed ups, right? So one is like basically when you even if you train on smaller sequences, that's one. And next is like basically you don't require any additional like memory overheads, like or at least significant overheads. So that's two together, like basically makes your training also very faster as well in this case. And if you look at like overall, right? So their performance peaks around I think 2x like the number of tokens. So probably in this case 5 and 2. So it's like your performance will be like really the best one at basically twice the token length. So probably roughly 1000 to 24, and in this case 2040, like as per the empirical evidence at least. And as I said, right, that it opens up more opportunities for like long context models as well, like which are more and also more important problems or at least interesting problems such as document summarization and so on. So now coming to like let's say different methods that are there. So rotary position method. So what they essentially try to do is they take a dot product between the positional encodings and the query key embeddings, and that's how like they inject the positional information. So they don't have add any positional encoding at the start. They have this learned positional encoding like which is shared across different layers, and you just take a dot product between this thing and then apply the regular attention. So if you look at in this method, right, computing this dot product itself like adds up like a bit complexity, and this approach is a bit slower as well comparatively. And one more step further, T5. So T5 basically builds on this rotary positional method. So at least the idea of T5 is that again you let's say inject this information in the attention values, but uh, you learn those values. So you learn those biases and like basically add those bias. So instead of taking like basically query key embeddings, you have this shared bias across all layers, and you learn this bias and just add to the query key dot product like that you have. So that's the thing in this case. And probably for this, so this experimental setups, all they try is on language models, so like autoregressive language models. But probably like later on, the authors have also released like maybe models which also probably for mass language modeling setup as well. So in terms of the approach, there is no difference as such. It just like yeah, the initial approach was like just presented with like autoregressive language models, just to highlight the same fact. And if you look at the speed, like the metrics or at least the graphs in this paper, so if you look in almost all cases where your training speed, inference speed, like alibi performs as good as sinusoidal, because both of them like are nearly constant, like with no runtime incursion, because like both are static or at least constant positional embedding. And in terms of training memory, also the requirements are pretty much like lower and yeah, compared to other methods. So at least that gives this speed up and boost on the training side. And yeah, so one thing in this case, like probably they'll say the existing methods that the evaluations are there, right? So the issue with existing methods is that they evaluate on non-overlapping inferences. And the problem with non-overlapping inferences that let's say when you have like this context of like longer sequences, then probably your perplexities would be lower, because usually let's say when you start predicting at the tokens at the start, right, your perplexity is higher, but as you keep on going predicting, your perplexity becomes or goes down at least. So this loss or at least perplexity like that you overall perplexity like start tokens only have most of the contribution. So if you, let's say, evaluate on non-overlapping sequences, and if let's say the sequence length is very high, then probably your perplexities would be lower because you have very few sequences to basically decode or at least like have the start tokens. But if your segments are like let's say dissected into very small fragments and you have very small context and you do the inference, you will get higher perplexities because you have more start tokens to predict. So I think in a way you're in short form or slide this one. So what authors try to do is like the same authors as AliBi paper, like what they try to do is like use sliding window protocol, and what they show by using the sliding window protocol, you can achieve like lower perplexities for smaller sequences as well, which was not like this before at least. So this is also a context for yeah. Maybe any doubts?
Just so for non-overlapping sequences, the perplexity is higher.
Yes. So the point was that just a minute. No, sorry, yeah. So the non-overlapping the perplexity is lower, but that is not a true estimate. Sorry, yeah, I know my bad. Yeah, because I think like there would be very few context windows that you will have like to predict. But as you keep on going for like more windows, you will get better, at least like more true estimate of the perplexities. And those are like the inconsistencies across different evaluations because everyone treats like this context length differently. So
Yes,
yeah.
bigger the sequence, the higher the chances of perplexity being high, right?
No. So probably what they say is like if your sequences are bigger, right?
Mhm.
So what their argument is like whatever the perplexity is, right? Like most of the perplexity value comes from like basically predicting tokens as a start. So if you have bigger sequences, right? So which means like let's say your context length would be then fragments would be smaller, right? So you
Mhm.
need fragments, and then basically you'll have less start tokens to predict, and that
Mhm.
kind of reduces the perplexity. But you have like the smaller segments, then your perplexity would go high because you have more high like start tokens to predict.
Okay, and why is that the prediction for the star token involves perplexity? Do you have any idea why is that so?
So I think the point being like let's say if you don't know anything, right? So eventually initially it would be very high perplexity, right? You don't know what to start with, right? But maybe as you keep on providing more feeding context, right? The model knows or at least like basically fits to those probability distributions and like basically knows like predicts and tokens, right? So that's like how their argument was like of why that might be the case. Like you will have higher perplexity.
Okay, so like based on the initial prediction, it is like pretty much fixed enough what the next context will be that the model will predict in that
Mm.
sense.
Yes, I think yeah. So that was
Okay,
the whole logic, yeah.
okay, thanks.
So that's one, and I think yeah. So for extrapolation as well during the inference, right? So I think I already mentioned this that learned positional embeddings might not be useful because yeah they are limited by the like positions that they can basically fit because they like just like learn the spurious correlation at least to a certain extent. And one interesting factor maybe that authors also I think in a way probably point out that let's say the learned positional encodings that you are having, right? So in this case, the models are trained on like basically huge files of text, right? So it is possible that at least for let's say certain words, model might have seen like that word in each position. So it's better able to encode like or at least position information about those words at least, right? Or at least previously map those things. But at least in let's say when you talk about language modeling, right, you don't want your model to basically just fix it on those patterns, right, for specifically, and that should be like injected more naturally rather than like basically learning this like correlations because those might not have always work. So at least that was like one reason like why learned positional encodings might not be better fit, and why do you want like positional encodings which can be directly used or just injected right away. So that was one, and yeah. So when you sinusoidal, the model cannot extrapolate to more than like a dozen tokens. Like so, as we saw, right, there's this like effect of exploding in this case. So after a few tokens. So far, any doubts? Let me know if there are any doubts. Okay, I'll move forward then. And yeah, so for the experimental setup in this case, I would say what they use is like they train a very small model. So like I think in total 237 million parameter model I think, and they have 16 layer transformer with dimensions of 1024 and 8 attention hits and feed forward layer of dimension of 4 1096. And yeah, it is trained on like 103 million tokens. So this like basically comprises of Wikitext. So this is the first setup of models, and then they also try to train like bigger models as well with this method, and also show that like on bigger models as well, this method tends to work very well. So yeah. So one thing like basically, I think I told you right, sinusoidal it's a constant vector learn non-learn vectors, and basically you just add those to the directly the transformer word embeddings that you get token embeddings. And in this case, if we look at, so they try training like basically at different like sequence embeddings. So probably it's like 5 and 2 sequence starting, and then basically let's say 1024 and 2048 and 3072 sequences. So yeah, input sequence. And as you keep on like basically looking at the graph as well, so if let's say the best performance was when k equal to 20, after that performance like basically starts deteriorating, and basically you see like the performance degrade in a way. And next thing, yeah, so rotary positional embeddings, right? So at least as rotary positional embeddings, as I said, right, it's just nothing but a dot product between the positional encodings as well as the query key, and then you apply the attention over softmax like scale dot product attention over it. So in this case, at least this embeddings were used by GPT-3 as well. So like at least those embeddings might be something interesting as well. And but one of the like maybe issue with this particular approach also would be that calculating this dot product is maybe computationally intensive, and still you have to maintain this learned positional vectors, right? And you have to like learn these vectors in the training. So you're just again like fitting to the training data in this case, and you cannot extrapolate to longer sequences. So that's the approach drawback of this approach at least. Any doubts in this rotary embeddings? So okay, then maybe I'll move ahead. And yep. So in this case also they see that this let's say the perplexity might be better than the sinusoidal, but yeah, it's still like tends to degrade later on. And probably if you look at like when let's say model is trained on like it's the 5 and 2 or 1024, improves the perplexity up to like 200 tokens in this case, and 100 tokens relatively, and that's it. Like, but you cannot like actually do predictions for inference beyond those. Like the model outputs are like really bad, and yeah, it doesn't make sense, and yeah, it fails. Next comes T5. So as I mentioned, right, so T5 also relies on the same idea, right, that you inject positional encodings in this each layers, right, each attention layer, and your T5 uses the concept of relative position method. So by a relative position method, that means that you don't want to add positional encodings to the word, but what you do is like you just learn this biases and you just encode this bias. So biases in a way gives indication about relative position. So maybe yeah, and we'll like see how that can be done, like maybe through static embeddings, but similarly applies for learned embeddings as well. So yeah, just maybe hold for a while. And whatever the biases that they get, they add to this like query key dot product, and yeah, in this case. And this is a learned bias, right? So it's a bit like at least slower as well because you have to learn this bias, and yeah, it adds to the computational overhead as well in the training compared to the other methods where you don't have to like backprop and like this thing, and like yeah, there's no, it is like not much extra training cost compared to this one. But this is the best method at least before AliBi, so yeah. And it can like basically support extrapolation till 600 tokens or 800 tokens depending on your sequence length, and yeah. But one of the like severe drawback of this approach is that the training cost is like twice the sinusoidal model training. Like basically when you have sinusoidal positional embeddings, let's say you take X amount of time, then it is 2x in this case. And that might not be feasible for training like this bigger models because yeah, I imagine like they're trained for like maybe 3 months and so. And if you add just like this one embedding component, it might be just like maybe taking month or two more as well. So imagine the computational overhead that you have in terms of like when training longer model, like bigger models, like really large scale models. And yeah, now like comes the AliBi method, and let's just see what they do. So if you look at AliBi, so what the idea at least is like to inject this positional embeddings, right? So what they do is they build upon the ideas from rotary as well as T5. So rotary, the idea was that adding attention. positional information to each attention layer. So that's one. Second, T5, you add this like biases to the query key value, right? And you learn this bias. So what they do is they replace this learned bias from a with a constant bias, and they just combine this two approach together, and that just scales up and works really well out of the box. So that's one, like, yeah, like the approach is very simple, combining like or building upon maybe a few things in the past, and yeah, it works very well bare bones. So yeah, in this case, this m is a coefficient or a scalar. So the idea is that, let's say, for different attention heads, right? So the idea of attention heads was that it captures, let's say, a different sort of information, right? Each attention head. So in this case, you add this m for different attention head. So maybe in some cases you might be attending, let's say, more towards the closer nearest tokens only, and in some cases you might be attending more towards the cases where, let's say, the query key relevance is very high. So attention values, like we see, they were like decide m values decide those factor in this case. Yeah. So m value, if it's closer to, let's say, zero, which means then your slope is very high, or at least magnitude is higher. And if it's like basically far from zero, which means it's more flat line, and basically then you have like equal or uniform attention basically across. So something similar to those logics, if you think of. And yeah, and what they do in this case is like, if you look at this is just a mask, right? So in causal language modeling, right, you apply a causal mask, right, basically of this. So what you can do is nothing but like you see, you can apply this mask m times, right, into this computational logic. So like just instead of multiplying it, just like logic of adding the mask, like, right, like with this causal inference and mask, and then just add it up, like that's it, with the actual query key computation dot product in this. And yeah, and why? Sorry, any questions? I'll just go. Yep, maybe. Yep.
No question. I just wanted to highlight that these biases they just can extrapolate to any sequence length of any tokens.
Yeah.
So this -1, -2, -3, -4 can go up to -16,000 also.
Yes. Yeah. So the point in this case is like the one, let's say for Q1, K1, right? So K1 would be zero. For Q2, K2 would be zero, right? So you just start like basically assign zero from where you start, and then you basically assign -1, -2 by like decrement of one, right? As you keep on moving further from the content, like basically the current token. So that way, you by having this function like flexibility, you can like basically extrapolate to however like longer sequence you want. And one thing, let's say, why your minus might be really interesting would be the following. So if you look at the softmax calculation, right? So softmax is nothing but e raised to x upon summation of e raised to xj, right? Or something like, let's say, all xi's, right? So when, let's say, you have this sort of minus in the e power, like power to the e, right? So e of like, let's say, x minus like some y, right? So eventually what you're doing is you're just dividing or scaling down, right, by those factors. So in this case also we are doing the same thing. So the idea here is that the closer you are to the actual current token, the less scaling you will scale down you will get. The farther you are from the current token, your scaling factor would be higher, like reciprocal factor, and like basically you will be like penalized more. So it's based on some distance metrics, and like that's how the logic is like for this having this negative values in this case, and how the computations like basically change. Yeah, any doubts?
So,
Or yep.
so is this method use only the absolute position information?
Uh, so this is relative positional information, right?
Yes, I'm not sure this method is relative encoding or
So this is
absolute.
like, yep. So just to make sure, so this is like a relative positional encoding, right? So the point being that absolute would be like basically, let's say, given some sequence length, right? Your maybe you just have like one pattern, right? And maybe in this case, what you're doing is you're just relying on this relative nature of the tokens, right? And just like having this, so which also provides you this extrapolation feature or at least benefit as well. So it would be a mix if you think of like, because let's say if you have like same number of tokens, right? So your positional encoding should be somehow absolute, right, in a way, or defined, because your matrix won't change.
Yeah, and maybe we should add that this is for only the query and key values. It is for the attention scores.
Yeah,
So
for attention scores and not the attention values. So, yeah.
yeah. So it is for the attention scores, and we are not giving any like a positional embedding at the beginning. It is given at every time the attention scores are created. They are somehow adding this bias value which prefers the immediate tokens which are near to the present token that the model is considering.
Yeah, I think yeah, that's true. I hope that answers your question as well, Shoshi.
Okay,
Yeah.
gotcha. Thank you.
Yeah, so that's like the one thing, and probably also if you look at this, probably by having this like scaling down factor, right? So what you're doing is also you're like basically normalizing your probability distributions very well, so that basically maybe like the spaces or like let's say the tokens or at least predictions are well separated, right? So at least one way to think of that would be also one by having the scaling down factor. So differences between like basically two like let's say probabilities would be a bit significant in this because at least boundaries would be sufficiently defined, well defined. So that's one. And yeah, so in this case, they like one other way would be that you can also learn this token right in. But the issue with this, like what they found out when you learn as well, or like you let's say assign some fixed static values, there's no difference in like basically this particular performance, model performance. So probably it doesn't make much difference like basically of like learning this scale because it will just add more overhead to the training and yeah. So that's one. And what they do in this M is like they come up with a simple formula of how you can assign like these tokens. So for let's say n heads, what you can do is like it's they just follow a geometric sequence, and the formula that this uses 2 raised to minus 8 by n. So for example, 8 attention heads, so you will have one half as a starting value, and this you will multiply by half like for each attention head. And when you go to 16 heads, it's just like by uh, 1 by 2 raised to zero point 0.5 and so on, like so similar idea. Yeah, so it is like the formula that they use, like, and that generalizes to like higher heads as well, probably. Yeah, and yeah, so different slopes might and like ensure that the model attends to entire context as well, and maybe not just nearer tokens. So that's one way, like how the m values would be. So if m is 0 or close to 0, it will attend more towards the near tokens. If m is higher, it will attend to uh, like at least the sorry, I think no, sorry, my bad. So if M is like basically closer to 0, right? So it will attend to more every token or at least if M is like basically closer to 1, it will basically attend towards the nearer token. So yeah. So yeah, and their values like the one constraint that they put is like basically to learn this values between 0 and 1. Yeah, M values. At least like basically assign. So that's one. And yeah, the implementation is fairly straightforward where what they do is like they just modify the mask matrix that you apply, like the causal mask matrix on the model with this like biases in this case. So it's just like a one computation that you have to do and like just replicate n times with all different elements here. And yeah, so for results, Akash, would you like to take over? Or, yeah.
Yeah. So basically, just to talk the good points about the AliBi architecture was, as Jay mentioned, that it scales the inference to a very huge number of tokens at inference time. So one very interesting idea is that you can train on smaller sequences and you can get good inference on bigger sequences at inference time. And also, if you see, can you show this diagram? Yeah. So can you zoom in? Yeah. So if you see here, you see these square blocks. They show models that are trained with the sinusoidal embeddings of different token lengths. So if you will see here that the first square block with around 20 perplexities is a sinusoidal model which is trained on token length 512. And similarly, you can see different different sinusoidal models of 1024 and 2048 and 3072. So the first very important thing is that these sinusoidal models, they don't really do very good inference whenever they're at inference time, whenever the sequence length becomes like 20 to 50 tokens more than the sequence length at the training time. So here you don't see any performance of these sinusoidal models in the immediate vicinity of the token length. But if you see the AliBi model, you can see that the AliBi model, which is trained with the token length of 500. So, sorry, Jay, you were saying something?
No, no. Yeah, sorry, go on.
So the AliBi model, which is trained on the sequence length of 512, you will see that at the sequence length of at the token length of 512, its perplexity is around between 19.5 to 20. But when you keep increasing increasing the token length at inference time, its perplexity keeps on decreasing. And to highlight the fact that the sinusoidal model, which was trained at the token length of 3072, the AliBi model, which was just trained on 512 tokens at training time, has lesser perplexity at inference time. So that shows that uh, when even models which in a head-to-head comparison with models which were trained with different sinusoidal models which were trained with much more sequence length, the AliBi model is still better when it comes to perplexity at training time, with even very few in very few number of tokens at training time. Yeah, so that's a very important thing to highlight here in this diagram. And yeah, Jay, let's go to the next image. Yeah, here. So in this diagram, the authors are trying to show that alibi at its they're trying to show what is the exact comparison between the performance when it comes to sinusoidal and the alibi models. So you will see that the alibi models with the length equal to 512 or even 1024, they give the almost same amount of perplexity when the total number of tokens are twice for in the sinusoidal model. So like in the left side, you can see that the perplexity is same for AliBi model trained with 512 tokens and the sinusoidal model trained with 1024 tokens. And on the right side, you can see that AliBi model with the trained on 1024 tokens at training time has uh, better perplexity even to a sinusoidal model trained with like sequence length of 2048 tokens, which is almost twice. So not only you can see the direct comparison here between the AliBi and the sinusoidal models, and you can in the previous diagram we saw that the AliBi model, which had yeah, oh, we can skip that. Yeah. And yeah, let's go to the next diagram. Yeah, here the authors highlight that for AliBi models, the peak performance comes around twice the amount of tokens that they were trained on. So on the left, you can see that for the AliBi model, which was trained on 512 tokens, it gets its lowest perplexity around 1024 tokens. And similarly, on the right, you can see the model that was trained on 1024 sorry, 1024 tokens at training time, gets its best or the lowest perplexity at around 2048 uh, tokens at inference time.
And just to add in this case that like this particular your CC100 plus Robota means that the model was trained on data basically that was used to train Robota and CC100 like basically Corpus part. So it's just like a mix of both data sets like combinations and then the model was trained on this. So it's a much bigger data and like yeah, just to highlight the fact. Okay, I just auto-regressive models. So Robota does not indicate that they apply this model like raw method for Robota in this case.
Yeah, and yeah, let we can go to the related work section now. So yeah, different authors like in the paper this Wenberg by and Hunter 2021, they try a radial basis function which again has trainable parameters. And yeah, so a very good thing about AliBi is that they don't really have any trainable parameters in the architecture. And another approach was long former, which they discussed. But yeah, they but to train long former, they had to train their sequences on much higher sequence lengths to get a very good result for long former. But here, even training on smaller sequences gives a very good result on huge sequences.
Yeah, I think long form also had to do some sort of like maybe modifications in their attention mechanisms and all. So that was like global and sliding window attention. So that kind of like let's say reduces the attention competition while still processing like the sequences and maintaining the performance. So that was one like point, yeah, in the long former. Yeah, overall complexity wise, it's still the approach was complex compared to this approach.
Yeah, I guess that's it, right?
So
Yeah, that's it from my side.
yeah, so this is a paper, and like let us know your thoughts and like what do you think about this. Yeah, the approach is very simple. Like just like combining two different ideas and just adding this in a matrix multiplication fashion and like that's it. And then applying exponentiation and like softmax based function in log scale and like yeah, that's like really appreciating factor of this like paper. I'd say like simple idea and very effective.
Yeah.
Yeah, so we'd like to hear your thoughts as well, like on this format. So, do you think like having this paper annotated papers are better, or like probably you would like prefer more slides, or like yeah, so that we can more adapt and like basically as per the needs of the group and like yeah, would love to